So thanks for your time to join me to talk about multiphysics analysis with CST Studio. Appreciate your time. Without due delay, let's get to the point. You know, I assume most of you are CST users, so by definition, you are familiar with CST Studio Suite, and you are expert in electromagnetic analysis. And CST is quite famous in this area, in the electromagnetic simulation capabilities, and you may wonder why we are bothering with considering other type of physics. So, but the truth is, for a long time, we don't have to, because computers were much weaker and people can simulate, were much simpler, and you can do one thing and do it really well, and that's wonderful. But today, things are changing. Well, don't get me wrong, there are still places for such dedication, for such do one thing, do it well dedication. But increasingly, people are designing devices with ever-shrinking margin, involve ever more complex physics. So for example, in the microwave RF and optical area, you may have to watch out for temperature-induced deformation to detune your filters. And for photonics, you may have to watch out for the deformation induced by heating and therefore change the behavior of your optics. And most lately, people are really working on the 5G devices. And this 5G base station, you have to design it carefully so that your device will get enough cooling and remain reliable and operated consistently. And especially in millimeter wave in the 5G domain, the size of the device are shrinking. So for example, the base station and antenna array are shrinking dramatically because the higher frequency. And they're much faster, but much hotter. And they're much more sensitive to heating. Sometimes you would have to use things like liquid cooling to maintain the temperature to an acceptable degree. And if we are undergoing some medical treatment, for example, this is hyperthermia treatment, like focusing some RF energy on a particular tumor, we need to understand whether the heating is effective, whether it's going to overheat the area that's not supposed to heat. So that's very important. We need to study that. Now, in the EDA and electronics area, which is maybe one of the area you're working on, and the last thing you want to have is such burned electronics. What you want is a nicely designed, streamlined electronics that work reliably and work cool. If you're in the area designing EMC, EMI area, then oftentimes the EMC issue is once the EMC issue is identified, you find out it was due to the lack of shielding. So in the above example, in this enclosure, through CST analysis, you identified the issue was actually caused by the power module, and you were cleverly put a shield in the internal vent area to block the radiation, and the problem solved. But the new question arises, whether the solution that you're providing, putting a filter there, would actually causing some heating problem, because once you put something blocking the airflow, the flow rate reduces and the device get hotter. And you need to analyze that. And fortunately, in this case, we find out by having such a filter, the temperature only increased 2 degrees. That's wonderful. But you do need to make sure that's the case. Now, if you're working even in charged particle dynamics in that area, you would encounter things like the particle crash onto your collector and then heat it up, sometimes significantly. You need to make sure it's cool. And if you think having lower frequency, less exotic situation, not accelerator, not particles, you don't have to worry about the other physics like thermal. Well, things may not be that easy because things like this switchgear, which undergoes very high current, like thousands of amps, the heating could be significant. You have to design it sufficiently. And if you're taking an airplane these days and you need to design your airplane robust enough so that under a lightning strike, the airframe, the stringer airframe, when subject to a lightning strike, it can survive the heating. So you need to understand how the current, the short current, would hit your device, or in this case, the body of the airplane, enough to causing trouble. So all of this tells us that we not only need to worry about electromagnetics, we also need to keep an eye on the other physics. I hope you are, as me, convinced that many times exploring multiphysics, particularly thermal effect of your device, is important and necessary. Now, talking about heat transfer, I have a few things to share with you. So first of all, I know many of you are CST users and you are EM expert, and you're familiar with electromagnetic phenomena. I want to assure you the heat transfer is an easier science in the sense that it is almost tangible, because unlike electromagnetic phenomena, which is invisible, you can almost feel the three modes of heat transfer, such as conduction, convection, and radiation. Now these days you must have spent a lot of time at home, and you must sometimes need to boil a pot of water. The heat need to conduct from your stove to the bottom of your kettle, and then the water become doing circulations inside. Usually you don't see that, but sometimes you do. They're doing circulation, and the pot gets hot, and they radiate out. So all three modes of heat transfer are playing at the same time. In most electromagnetic related applications, now heating is usually generated by the electrical current inside your solid parts, such as antennas, such as your IC packages. And then the heat travel on solid through conduction. It's very easy to understand, right? But once the heat travels to the exterior of the surface, when you encounter your neighboring fluid, be it air or some other cooling fluid, you need to get out of the surface by convection and radiation. Now you may be starting to get intimidated by these new concepts, but don't worry. There are things that we can use to help. In this case, they are just, we can use resistor analogy to understand how thermal science works. So if we take a look at this typical electronics, the heat is generated in the die, and through the resistance, the resistor by conduction, it goes to the chip surface and migrate to the heat sink. On the other path, it will go to the PCB board down below, and the heat will go to the air by natural convection if there's no other heating mechanism there, and will radiate to the environment. So you can imagine, or conceptually, consider the heat transfer path as the conduction, convection, radiation in such a simple circuit, I'm sure you can solve this almost in the back of envelope, no problem. So thermal science, I say, thermal science is relatively speaking easy to understand. You just need to understand these three modes and understand how they put together in a circuit like situation. But there's one question, which of these resistors are more important? Now I would like to give you a analogy here. Hopefully it's helpful. Let's say you have a water tank and your heat source would be like a faucet or a valve that constantly fueling or fueling your water tank. And you have three valves: convection, conduction, radiation. Okay, so you're draining the tank as you're fueling it. When the tank is full, your convection, radiation, conduction has to, well, the amount of the giving out has to equal to the heat source going in to reach that state. Now, which valve open wider is the one that's dominant the effect. Yeah, so you see the color I used. I had the convection radiation in blue, but the conduction in gray color. There's a reason for that, because the conduction happens inside solid. Like the picture we're showing over on the right, heat generated inside the solid, it doesn't really leave the solid. It needs to go to other places on the connected solid. Eventually, when it's reached the surface, they have to leave your system by the convection and radiation. So you can design your system, have a nice conduction inside, but in the end, you have to deal with the convection and radiation. Now, this is still maybe a little, conceptually okay, but hard to gauge which one is important. Now, I'd like to give you another help here. Let's consider everything, all the resistors, in terms of this famous heat transfer coefficient. We can write the Q, which is the heat conducted. The analogy would be your current with H equals to H times area times the delta T. And we can write that equivalent term in 1 over R, like conductance. And the temperature difference will be your voltage difference. If you write in here, you're starting to feel a little better about how we can gauge these three valves, how they can leave your system. So let's give you some practical numbers to work with and to understand how it works. So in CST, there's macro collections. If you go to home, macro, calculate, and heat transfer coefficient, you will see this calculation of heat transfer coefficients. I give you two examples here. One is the so-called natural convection. There's no cooling devices involved. A plate, vertical, maintained at somehow at 42 degrees. You will see the heat transfer coefficient is 4. And on the right-hand side, the same plate, same size, 100 by 200, have 5 meters per second flow or air flow blowing over it. The heat transfer coefficient is 26. So you can see how relatively speaking, what the valve looks like. And if you take a closer look at the one on the right, the radiative heat transfer, which is the second valve on the right earlier, is almost the same, or in this case slightly bigger than the convection one. So this is the key. If you're modeling something in natural convection, which means there's no active cooling devices involved, you must model radiation. If you're modeling forced convection situation, like if you have a cooling fan, liquid cooling devices, you don't have to worry about radiation that much. You can still turn it on, but many people turn it off, not modeling that, because that could be your buffer or your design margin. So much for the fundamentals, and hopefully give you a good feeling of how the heat transfer works in general. Let's drill down to CST Studio itself. We say we have a MultiPhysics studio, or CST Studio has a MultiPhysics studio. It really has a family of 4 solvers. Today we will spend a little bit more time on the first 3, which is all the thermal solvers. Our sister brand, Abacus, would have much stronger capability than our mechanical solver, the structure mechanical solver has. So it has the steady state thermal solver, transient thermal solver, and the conjugate heat transfer solver in the thermal part of the MultiPhysics studio. And here to our title here, they share exactly the same GUI. In other words, if you know how to operate CST already, you know how to operate the MultiPhysics studio. There's no difference in terms of operation. I intend to do a live demonstration later on in the webinar if we have enough time to show you how it works on live. But you will see whatever you have learned before would apply here in the heat transfer and MultiPhysics studio. And here we wanted to point out a significant advantage when using MPS is that the losses that you're computed through your EM simulations from Microwave Studio, EM Studio, Particle Studio, and most recently we introduced the PCB Studio IR drop calculation loss transfer to MultiPhysics Studio. So the loss are accurately mapped over to the MultiPhysics Studio. It's not like a lumped number. It's a spatial distribution that help you to accurately capture where the loss occurs. So one GUI, MultiPhysics. Okay, so those are some examples I'll show you that utilize these solvers. There's some distinction between these guys. I will show you in a live demo. Now, some key features in the thermal simulation. I want to just quickly go over them, and I would not delay jumping into the software and show you how it works. First of all, the meshing. You must have used CST's famous hex mesh. Now here we're using a technology very similar to that. We actually, as a matter of fact, we use that as a starting mesh. And if you have used one of the Emacs T-solver meshing called TOM, you must be familiar with the cell lumping capability, which can reduce the unnecessary cells in the area that nothing really happens. Similar here, we're not cell lumping, we're refining, but the end results are very similar. You end up with a mesh that's concentrated in the area that's needed and coarse in the area that's not needed. And you can use your EDA import to simplify your geometry for thermal simulation. I will show you in the live demo in a moment. We added a new feature in 2021 that help you to accurately capture the neighborhood of your key chips. And we support JTAG2 resistor thermal model, and you can model things like a cooling fan, and you can model things like a finger guard or grill with a flow resistance object instead of modeling them in detail. You can model the thermal interface material, TIM here. It's not a person, it's a terminology for thermal interface material. And if you're modeling something at high altitude, you can adjust that automatically. And we support multiple fluid to do liquid cooling. And we can, as I mentioned, significant advantage here using CST is to accurately map the loss information from Emacs simulation to thermal simulation. And lastly, not least, we support high performance computing, including GPU support. So if you already get GPU for your EMAG analysis, that investment can be used here as well, which is great. Okay, so just a little bit more words, a couple more words about these capabilities. You see the meshing is similar to the one that you're familiar, push button, auto repair, non-watertight geometry, self-intersecting surfaces, handle a large number of parts. You've seen that many times in CST. Import your PCB board, and most importantly, in a lot of times thermal science, you actually have achieved very little by model everything in detail. So we offer this 3 simplification levels, allow you to not simplify layer by layer, and simplify all of the PCB at once. I'll show you in a moment. And direct thermal link. So I've covered this a few times now. Hopefully you're convinced this is the right way to do, because you do need to know where the actual heat loss is. So having an accurate mapping is very, very nice. And we model all 3 modes of heat transfer. I hope you still remember that we talked about there are 3 modes, and only 3 modes of heat transfer: conduction, convection, radiation, and you must include radiation if you're working on natural convection situations. So we include all of them in the thermal solvers, so you should feel very confident using them. This is a compact thermal. If you're not familiar with it, it's basically modeling a chip with simplified JTAG standard to resistor, modeling a fan, flow resistance, thermal interface material, and so on and so forth. So I'm not going to spend too much time because I will show you how it works. I will also get a chance to, hopefully, show you how the different fluid would work. And then automatic adjust air density and fan curve based on your altitude information to account for people like these guys. No, that's not real. That's just for fun. In reality, there may be devices mounted at high mountain, carried on an airplane that have a high altitude, the air density is less. We automatically adjust that. All user have to do is to enter your altitude. We do the rest for you. And last and least, we support GPU. Okay, so as I promised, not without due delay, I'd like to show you 2 examples today. One is a nice switchgear. I need to thank my colleague to produce a nice model of the switchgear. This is a low frequency device that carries thousands of amps. We need to see how thermally it works, and we can study how a short circuit situation, whether it will withheld or it will successfully melt away to provide the circuit breaker capability. So you can produce results like this with MultiPhysics Studio to show the streamline and temperature plot. And the second example I'd like to show you is a smartphone. Everyone had one of those. This is our creation. No, it's not working, by the way. In other words, it's not going to receive calls or browse internet, but it does allow us to show you how it works thermally, electromagnetically, and so on and so forth. So my colleague gave me this nicely designed phone to demonstrate the thermal situation. Now there's a new thermal challenge for this kind of devices. The weak link is actually the human being, that we are sensitive to too hot of an object. For example, our skin are not okay with temperature that more than 45. Usually say 30, 43 are the upper limit that you can actually tolerate for holding something long enough. So we'll see how can we analyze the phone and do some parametric analysis to ensure that we have sufficiently comfortable working device like this. Yeah, so we can show you how to do some material study and identify what are the key factors here. Okay, so without due delay, as I promised, I will show you how it works on the fly. Okay, so to save you some time, I am preloaded this demonstration model of the switchgear. It's already built for the EMAG analysis. This is a low frequency LF solver, and we have 3 phase here, phase A, B, C. They each of them carry 2000 amps, very high current. Now, if I wanted to analyze this device and then also analyze the thermal heating effect of this device, what I can do is do this. You go to the schematic. Now I have this one already built. I will use this for a reason, but I will show you in a moment. What you want to do here is go to the simulation project, EM thermal coupling. Now we support unidirectional and bidirectional coupling. In other words, if your device are temperature sensitive, the property change with temperature, then you can use bidirectional link. So the temperature map can be supplied back to the EM solver. But today's demo, I will choose the simpler of the two, the unidirectional coupling. So when I choose that, the software will think a little bit and ask me, hey, for your EMAG analysis, what do you want to do? So this is the first dialog box popping up. It generates this nice loop here and asks me what EM solver I want to use. So this is a low frequency simulation, and then the solver is the frequency domain MQS solver. So I don't have to explain too much here. You are expert in this area. And then here I can link to the master model. In other words, if I make some changes to the master, it will propagate to this what we call a sub-project. So I hit OK here. Then it asks me, hey, what do you want to do with your thermal project? Which solver you want to use? Let me explain a little bit about these solvers, what the difference are. I'm going to use the conjugate heat transfer solver in this case. The first 2 solvers are still very, very useful. They are conduction-based solver. In other words, they solve accurately what's happening inside the solid at the fluid and solid interface. At the surface, you need to make some assumptions of the heat transfer coefficient. Remember, we have a calculator for that. But usually, the surface are not that simple. There's no flat surface in the switchgear, for example. It's really hard to estimate what that is. So no worries if that's describe you. You can use the conjugate heat transfer solver with no need to assume anything. You solve the flow. And the heat transfer together. That's why it's called conjugate. So I'm going to hit OK here. So the last question they asked me is what frequency you want to link this to. So this is a European device, would be 50 hertz. You will see that dialog box popping up very shortly. It's creating the 2 simulation project, one called EM2, one called Thermal 2. Okay. So I'm using the wizard. Now, don't get me wrong. There's nothing prevent you from actually setting this up manually by yourself. So all you have to do is make the 2 project and link them. The wizard help you to link them and do the logistics for you, but there's really nothing prevent you from doing it manually. And here it asks me about the frequency and ask me about this scaling factor. Let me hit OK, just not waste your time. Explain the scaling factor. Let's say you're in a high frequency simulation, usually your input power is half watt average power. 1 watt peak power. So in that case, if your actual input is not half watt or 1 watt peak power, it's actually 5 watts, for example, you need to scale it to the correct scaling, using the correct scaling factor. In the low frequency simulation, usually you enter the actual amp or actual voltage. You don't need to scale it. You can just leave it at 1, so don't get confused. So the EMAG part is identical to the master project in this case. There's no change, so I'm not going to discuss too much. I'm actually going to close it. The thermal part, now let's take a closer look at the thermal part, is preset to be using the solver I chose. And there's a couple of things I need to do to make it working thermally. First of all, I need to make sure all the material have thermal properties in there. Many times when you are so eager to do EMAG analysis, you say, okay, let's set the epsilon and mu, all those material and conductivity sigma correctly, and you don't need to worry about the thermal parameters. But when you actually doing the thermal analysis, you need to make sure they do have the correct property. For example, if I select this part, and this is the part, and has aluminum assigned to it, and fortunately this is from the library, we do have the thermal property in there. No need to worry about that. But I say this is there's no cooling fan in this case. We need to model radiation. So I need to modify the thermal property ever so slightly. So I need to go into here, and this is the aluminum object. You right click on it and go to the thermal property here, and go to the thermal property, enter something called emissivity. Emissivity is a number between 0 and 1. Calibrate the surface, whether it's really good reflective mirror-like surface, which is almost 0, or it's a black surface, which is 1. So usually the material like to take the advantage of radiation. You would design it with higher emissivity to radiate more than the mirror. You don't want to polish it to a mirror-like situation. And if there's some copper copper inside, I can change this to a better emissivity as well. That's all you have to do. All the other property, thermal conductivity, density, and thermal capacity, 3 numbers are pretty much all set if you use the library material. Now, this is a switchgear. If you're working in this area, you may know this one was actually sealed and filled with pressurized SF6 gas. It's not like your normal air because that's too easy to break, to cause breakdowns. So what you can do is to assign the internal of this device to have a different gas than the background gas. So let me show you how that works. So what you do is you rotate this enough so that you're easy to select one of the internal surface. So you pick here, it says fluid domains. You hit new fluid domain. It asks you to pick a surface that's inside. If this is the internal surface, I can just double click on this guy and then press enter. You don't need to select all the surfaces. Just one will be enough. The software will find the other connected surface and make sure they're in the same so-called cavity. And then I can say, okay, so inside this cavity, I can load a new material here. And I'm going to use SF6. It will filter. I have this preloaded, pre-built. It's in 0.5 megapascal property. You load this one, and you can rename this one to something make more sense to you. For example, SF6 would be usually the gas that you fill in. Hit OK here, and that's all you have to do. You already defined this inside cavity with the correct material, so to speak, a gas in this case. And let's take a look at the settings here. This is set to fuel source EM2. This is actually what the wizard is doing. The wizard set your losses to be pointing to the EMAG solver, which was created. However, I don't want to waste your time. I don't want to solve this. It takes about 5 minutes to solve, but even that is precious. I can go in here and change this to EM1, which is the one I already pre-built. And I can say, okay, this is the EM1, and it will find the loss there, and it will say, okay, I find it. It's a low frequency solver, 50 hertz, and a scaling factor of 1. So I can hit OK. So this one will lit up. We'll say, okay, I find it. And then the next thing is I may need to close the two openings. Actually, in this case, I probably do not have to. I can have my solution boundary over here, so this will naturally sealed. But in case you do need to close here, because I wanted to separate the air and the SF6, what you can do is select some convenient edges here. Like here, I can go to modeling and change this to a selected edge to be a curve. And then I can say I wanted to construct a surface. Oh, actually, I want to do this, extrude the curve. The curve is selected. The direction I learned last night need to be a negative number so that it's pointing to the other side. I said, okay, so this will be closed. This side will be closed. So it doesn't matter what material this is. It's not going to affect our answer. We can just leave it there, give some random material or same material as the other one. I'll do the same. This time I'm a little smarter. I'm letting the software to pick the edge chain for me. I can say select the edge again, and then I would extrude the curve and then create another one of this. It gives you this, this is not right, so let's change this back to something like copper and hit OK. So this will be another object covering this surface. So I'm really all set, almost here, except this body has probably wrong material. I'm going to assign this to a copper material as well. So I'm all set here. Now the next thing is to set up the background, how big it is. By default, it's not bad. I think I can deal with that. The two sides here and here are, there's extension to other places, so I can leave them at 0 touching here, and then there's some space up and down here, and around the geometry, I'm okay with that. And then for the boundary, by default, they're like wall. That's not good. We want to have open boundary, so the air outside this device can go in and out. And then I can say maybe on the two sides that with touching the lid, I would say adiabatic, means no heat transfer here, only heat transfer opening over here. Then I'm really all set here and can do a save here and start solving. I will solve it at the background. I'll show you the second example because we're about running out of time because I really have exciting thing to show you. So I'm going to kick off the solve. The reason I want to solve this is I want to show you a few things. A little dangerous, but let's say maybe hopefully it's okay. I'm going to turn on radiation, turn on gravity. Sometimes people say, why you need gravity? Because the hot air goes up. That's because of gravity. We need to tell the software which direction is the gravity so the hot air can go up. So I'm really all set up this gravity turn on, turbulence model automatic, and the environment temperature 25, radiation turn on, and I can kick it off. And note here, I have a steady state, meaning if the thing is operating at this ampage, what's going to happen? And I can do a transient simulation, meaning if there's a short circuit, which is the result I want to show you in a moment, what happened with the air and the temperature if I have a short circuit situation, I can do something like that. But I'm going to kick off this guy, let it run in the background, and I'm going to switch to the second example. In the second example, it's a smartphone, if you remember. So I'm going to start from scratch. You will notice even more dangerous. So, but let me do it quickly. Now, I want to do a pure thermal analysis. If I don't need to link the EMAG part, I can just do a pure thermal analysis as if you are using a thermal analysis tool. No problem with that. And then, so you start with an empty project and then change the unit to millimeter, usually good for the phone. Change to something that you used to, like Celsius, and we don't have to worry about these two parameters. Now we can start by importing the geometry. Let's import the step file. You can see we can import many formats here. You go to step file, and I go to my quick access thermal. I hope I have the phone here. I can scale to the current unit and then do open here. So the phone is bringing it in nicely, hopefully. And then we can take a look at the composition of this part. And first of all, I want to turn off this working plane for now. And I can hide the surfaces, the back surface, to see what's inside. So that's a back cover. I can Control H and hide it so we can see what's inside. Now we notice there are some pre-built PCBs. I want to show you the PCB capability. So I will change one of the PCB as a placeholder. Oh, there's some lumped elements and ports. Those are for EMAG analysis. Let's just get rid of them for now. Let's go to here, the phone and PCBs. So this is the one that I wanted to replace with the actual PCB simplified version of that. So I change this to a placeholder, and then I will use that as a location or template to bring my actual PCB in. Going here, I go to the import again. This time I will go for a LDB++ import. Let me go to my quick access again and then go to my PCB board file. So in this PCB board file, you have now, as I mentioned, you have the option to really simplify the complicated traces with a one switch simplification here. And in 2021, there's some exciting feature here I wanted to show you. You can activate the area restriction as you do with the EMAG analysis. What this allows you to do is to keep the local detail of the key chip. For example, this is U1 and this is my key component. I want to keep the local details. So what I do is I can say new rectangular selection here and then draw a rectangular box. I will keep some distance from this device, and that's it. Now I can switch the components and define my heat sources. Here, for example, I can say I want to define some U's. I want to define the U1 to U4, U5, U8, for example. Let me see if that's the one. Yes. And then I can put them all over. I can say, okay, U1 is the key, is the app chip in the phone. U2, U3, this is 0.05, this is 0.0, this is 0.1, and the other are 0.15, this is 0.05, oh, sorry, 0.15, for example. It doesn't matter at this point. I can just show you the process. You get the idea. So I can just say, okay, here, sorry, my bad. This one has a 0. I can say this is 20 mil, 20 mil. Okay, now we're good. Now in peace. Now I can say, okay, finish import. Give me some warning and informational message. Can ignore that for now. So this message, this new PCB simplified version will be coming in here. May not be positioned right. We can align them together. But let's take a look at this newly imported PCB. You see we have the heat sources predefined already, and the heat sources is also assigned according to our specification, 1.2 watts, 0.05 watts, etc. And then there's some details that's already kept next to our key U1 device. It's not simplified. They are exactly the way it is in this neighborhood. And the rest of the board are simplified. If you look at the property, they're averaged based on the copper contents in the PCB. They're anisotropic properties. So this is really good. I'm happy with this. So now I'm going to do is to position this to the correct place. So placeholder, I need to find my placeholder. Okay, just a second. Let me see if it's still there. Okay, maybe it is PCB. Oh yes, it's right here. Sorry, what I'm doing. Okay, so I have the placeholder and my new PCB. You know, I can hide unselected. So I hide all the complexities there. And now I can select my newly imported PCB and use the align function. So I wanted to align this surface with this surface. No. Okay, so the bottom surface, that's better. Okay, I can align this together, and then I would say, okay, this edge, align with this edge. All right, so I'm all set. I'm not going to do some operation at the moment. The only thing remaining to do is to put this guy at the right place. For example, I'm still shifted slightly if I'm having this too. So this is below what's need to be. That's easy operation for CST users. So I'm not going to spend too much time. I'm just going to do it. You can watch a little bit. I just pick 2 points from here to here, and then I will be able to select this one and do a transform operation. It will come to the right place, and I'm all set. I'm all happy, no operation. I can delete the placeholder and then drag and drop this one into the right place, the PCB and the phone here. That's all. That's all we have to do to set up this problem with all the heating parts and simplified PCB can repeating this process so that it will complete the model. And the process that you're doing this is very similar to what I did earlier with the other project. So let's take a look at the other project, see if it's solving. So the CST started to iterate. And during the iteration process, we can observe the convergency. So starting to running a couple iterations, and during the iteration process, we can actually see what's going on. If you go to the 2D, 3D results, do a refresh, you should be able to see what is the temperature at this moment during the solve process. Take a while for the thing to refresh. During that time, I would like to show you the actual result I got. So here's a little story. I solved this case entirely very nice with no problem. So the only problem is it has a loss of mesh to model everything and to solve the flow. But it wasn't too bad. I can see in the area where it needs to be refined, it refined. It doesn't refine 10 million cells. And then if I look at my log file, I want to point to you, this model take about 4 hours, 11 minutes. That's with 1 GPU systems. Though that's nice. But one thing I mentioned to you earlier about heat transfer coefficient, if it's nice that we can do this a little faster, if I swap out the material, like my colleagues say, okay, so this model is quite nice, but I want to use a different material for a plate. inside this one is actually one of the plate that I will show you in a moment. Show you this one. One of the plate with holes here. You want to use a material, plastic material instead of steel, which have better heat transfer, and see if that works. Now I can spend another 4 hours, or what I can do is to extract the heat transfer coefficient from the 10 million grid size model. What I can do is go to the monitors. I pre-planned the glass and the frame. I can extract the heat transfer coefficient. They're about 11-ish. So I put that in here in this model. This, remember, is not CHT anymore. It doesn't solve flow, so it's much, much quicker. You can assign this as a thermal surface condition here, top and side. They're all 11 right now. And if you do that, you can get the solve down in about 11 minutes. So you can study what's happening inside my phone if I swap material in 11 minutes instead of 4 hours if you use this approach. We can do this only because this phone, inside the phone, there's not much air. You can assume that's pretty true because there's not a lot of room to move around. That's why we can do this. We can assume the outside surface is convection and radiation dominant, inside is conduction dominant, and there's really good application for this approach. By doing so, we're able to see if I continue to use the metal material as I did before. Let me go back a little bit and select the whole surface. So you will see the temperature, it will be the similar temperature that you're getting. Is about 49, the maximum temperature, which is, higher than 45 comfortable temperature. We need to do some work, but not too bad. However, if you switch the material to plastic like ABS, the temperature really, the surface temperature goes up to 63. And that's not really good for holding it. It's going to feel very hot and you don't want to hold it. So that illustrates the fact that in modern electronics, in handheld devices, thermal conduction and thermal spreading are really playing a key factor here. So for the other model, I want to show you the results, which I already got. For the steady state results, we can solve for speed and temperature as you see on the screen. You can do all the same operation that you did before, but this time you'll see the hot plume showing up. And for the transient analysis, I captured a few pictures here because it will be slow if you play it over here. So for the temperature change, it's like this. So the temperature really heating up for the short circuit analysis. You can see it's starting from the contact property and migrate to other places. And here is the velocity contour or isosurface plot. And here is the vector plot. And you can see the vector or the airflow starting to get worked up by the sudden heating of the device. Okay, so I hope I covered most things. I'm about to run out of time. Hopefully you find this interesting. I want to give you a quick summary before the question and answer session. I hope you come to the same conclusion as I did. The MultiPhysics Studio is really a cool tool to explore the thermal effect. And the part of the reason is that you are already a CST user. You know how to operate the tool very effectively, so you can take the most advantage of the tool. And the family has 4 members. The first 3 are thermal solvers, the last one, the mechanical one. And the best news of today is it is already included as part of the CST Studio Suite. So you can play it on within your CST. So that's conclude my presentation. Sorry, I'm a little rushed at the end because I need to stick with the time.